Hi guys, so today we're going to be looking at optical isomers, which are a type of stereoisomers. So we're going to be taking a look at a few properties of these. So these are going to rotate plane polarized light in equal but opposite directions, which is termed as optical activity. And the details of all of this are not in our syllabus. The next point is that they must have at least one chiral carbon attached to them. Now a chiral carbon is a carbon atom that is bonded to 4 different groups. So the carbon that I've highlighted over here in white is going to be classified as chiral because it has 4 groups attached to it. A, B, C, and D are all different from each other. So because of that, this carbon, the white one, is going to be chiral. The next point is that they form non-superimposable mirror images of each other. So what they do generally in examinations is they might draw out a simple structure like this for you. Now, as you can see, the carbon in the center is chiral because it has 4 different groups. There's a hydrogen, there's a chlorine, there's a bromine, and there's a methyl group. So since all of these are different, this carbon is going to be a chiral carbon. So normally in examinations, they ask you to make this optical isomers clearly showing the bond notations. Now, this is going to be tetrahedral because there's 4 regions of electron density. And if you're confused about bond angles and 3D bond notations, there's a video on that, so you can go watch that. Now, if you draw the 3D bond notation for this is what you're going to get. Now, what you're supposed to do is you're supposed to make a dotted line over here, which represents a mirror, and you're going to reflect this compound. So this bromine is going to come over here. This chlorine is going to come over here. And the carbon, hydrogen, and methyl group are going to stay in the same position. So this is the diagram for the non-superimposable mirror images that you can have. And one important thing to note is that these isomers do not have any plane of symmetry. Now we're going to be taking a look at a few examples of optical isomers. So let's take a look at this structure. If you redraw it, you can see that this carbon is the central carbon. So it's bonded to one hydrogen over here. This OH group is in brackets, which means that it's bonded to the previous carbon, which is the white one. So you have an OH group over here. You have a methyl group attached over here. And you have an ethyl group over here. Now, since you have 4 different groups, this is going to be an optical isomer. So let's take a look at the next example. So we're going to be examining each carbon separately, and we're going to be deciding which one of these is chiral and which one of these is not chiral, because in MCQs they usually give you large structures like this, and then they ask you how many chiral carbons are there. So we're going to be looking at how exactly we identify that. So let's take a look at this. This carbon has 3 hydrogens bonded to it. Now the criteria for a chiral carbon is that all the groups need to be different. Since in this case 3 of them are the same, this carbon will not be chiral. Let's move on to the next one. So the next one has 1 hydrogen, 1 methyl group, 1 chlorine, and this entire big group attached to it. Now all of these groups are different, so because of that, this one is going to be chiral. Let's move on to the next one. So this carbon has 2 hydrogens attached to it. Now since both of these groups are similar, this will not be chiral, and it's the same case for this one. Now this carbon over here has 1 methyl group, 1 hydrogen, this group, and this entire big group attached to it. Now since all of these 4 groups are going to be different from each other, this is going to be chiral. Now if you move on to the next carbon, this already has 2 hydrogens attached to it, which are same. So because of that, it does not have 4 different groups and it's not going to be chiral. So this molecule has 2 chiral carbons. So this is the next example that we're going to be looking at. This is the skeletal formula. If you draw this entire thing out, this is what you get. So this is the first carbon. It already has 3 hydrogens attached to it, so because of that, it's not going to be chiral. And the next 2 that you have over here, they also have 2 hydrogens attached to them. So these will also not be chiral because it's the same group. However, if you take a look at the next one, it has 4 different groups. A hydrogen group, a methyl group, an ethyl group, and a propyl group. And this is the carbon over here. The next two carbons have more than one hydrogen attached, so these are not going to be chiral. So generally, when in skeletal formulas, if you have something crossed out in this way, like a structure similar to this, it is usually chiral. But do take a look at it and examine it carefully just to make sure. Now we're going to be taking a look at a skeletal structure. So these carbons over here, and these carbons over here, and even this carbon over here have double bonds attached to it. So whenever you have carbons with double bonds, you're just going to ignore them when assigning optical isomerism because they cannot have 4 groups attached to them. So don't even take a look at them, just ignore these. So starting off with this carbon over here. This has an OH group. If I make a carbon over here, if I write down CH, this has an OH group attached to it. There's one bond coming out of here and one bond coming out of here, and different groups attached to each of them. So since all of these are different, this is going to be chiral. Let's move on to the next carbon. Now this carbon over here has this group attached to it, this group, and one hydrogen. Now since all of these are different, this is going to be chiral. Over here, this carbon has a hydrogen attached to it. It has this group and this group attached to it. So because of that, this is also going to be chiral. And the last chiral carbon in this structure is going to be this one. Now this has one hydrogen attached to it. It has this group attached to it. And it's also going to have this group and this group attached to it. So it has 4 bonds coming out of it, pointing at completely different groups. So this is also going to be chiral. So this structure over here has 4 chiral carbons. Now the formula is similar to the formula that we talked about in the previous video, 2 to the power n, whereas n refers to the number of chiral carbons that you have. So since in this case you have 4 chiral carbons, this compound will have 2 to the power 4 isomers.